Hi, and welcome to video 2 of 2 for Chapter 6. In the previous video, we talked about Gauss's law, which, if you remember correctly, looks something like this. If you make a surface, a Gaussian surface, and look at the electric field that passes through that closed surface, that field is due to the charge that's present. And typically, again, we look at the charge density when we talk about that. Now, what I'd like to do today in this video is to talk about some of the implications that Gauss's law gives us, specifically with respect to conductors. Now, remember, conductors are generally metals, and metals have a lot of free electrons. And it's the free electrons inside metals that allow electricity to pass. It's also the free electrons in metals that allow metals to have the specific heats that they do, the very low specific heats. So, that said, what we're talking about now, that is in Chapter 5, Chapter 6, and to some degree in Chapters 7 and 8, are situations that are called static. They're electrostatic. Now, in a situation where you're dealing with electrostatics, generally what we assume is that charge is stationary. And the amount of charge does not change with respect to time. So we'd say something like, dq dt is equal to 0. Okay. So I want you to, at least to begin with, to think of a sheet of charge. So let's pretend you have a sheet of charge. Let me draw it here. We'll say on edge, maybe it looks something like this. So, this right here would be my area of charge density, sigma, which, if you remember, would be, charge over area. Okay. And, if you were to look at this on edge, it would basically look something like this. So what I'd like to do to begin with is to use Gauss's law to calculate what the electric field due to a sheet of charge is very close to the center. Now, we've actually already done this, not with Gauss's law. We used arguments with respect to vector calculus to find this by integrating over a plane. And so what we're going to do here, though, is to use Gauss's law to do it. And, there's a method to this. You're going to see why we do this. So I want you to think about, say, close to the center here. What we're going to do is we're going to cut a chunk through this. So let me see if I can kind of simulate this chunk we're cutting. Yeah, it's not a bad guess. Actually, I'll be pedantic about it. We'll do it like that. And then let me just sort of copy this guy right here. For a template. And what I want to do is to sort of pass this cylinder, this Gaussian cylinder, if you will, kind of like when we, looked at a long straight wire. We're going to pass this through the sheet of charge out the other side. So here's the other side of the cylinder. It's kind of obscured partially by that. Now our cylinder, we know, has end caps. I'll call this S1, surface 1. This is surface 2, and this right here would be surface 3. much like the previous example that we did in the last video. So if I were to sort of section it on edge, it would look something like this. It's a lot easier to draw. And, on this side, S1, on this side, S2, and, the barrel of our cylinder right here is S3. So, so let's think about what we expect the electric field to look like. Well, if you think about this as being a line of charge and not a sheet of charge, we know that, using arguments that we've used before, that at a point above our sheet, you would have field go this way, you would have field go this way. The magnitudes of the field would be the same. But so what that means is the sides cancel out and you end up with an electric field that points straight out. So really all a sheet of charge is a whole bunch of lines of charge that are placed side by side. So if you think of looking straight down at that little sheet of lines of charge, they kind of look like point charges, which means that if you were to pick a point above and you look at this line of charge, well, he's going to have an electric field that points this way. You look at this line of charge, which is equal distance to the other side. It's going to look like that, which means, again, you end up with an electric field that points straight up. So let me just clean this up a little bit. Now, so what that means is that I can, make a pretty solid guess that, my electric field is going to come straight out of the sheet like this, and it's going to be on both sides, obviously, like this. Okay, so if you think about surface elements, for our little barrel here, we have a surface element that points out, radially outwards from the axis of the cylinder. We have one that points this way, and then on S2 over here, we have one that points this way. So what that means is that the barrel part right here, which, if you were to think of it as sort of pointing out of the screen at us, well, that's going to be at right angles to the direction of the electric field. So when you look at its contribution to the flux here, the contribution is going to be 0. On the other hand, unlike the long wire example that we used, now it's the end caps that matter. So it's really the end caps here that we're going to use to find the field. You have a normal vector here. You have your normal, surface normal pointing out from the end cap. It is, again, parallel to the electric field. And if we center our cylinder on this, what that means is that whatever the electric field is on this side is going to be the same as whatever the electric field is on this side in magnitude. And it should be uniform all the way across the front of our disk. Now that's kind of nice, okay? So next, let's think about the charge that sits inside of our little surface. It's this right here. Now if you look at this right here is going to have the same area as the end caps are, because you're carving it out of basically like you've stuck like a pipe through it, right? So, the hole on the end is going to be the same as the hole that's been cut out, right? So what that means is if you look here at your Gauss's law and you think of having, 3 distinct surfaces, which I'll just sort of abbreviate as the integral S1, the integral S2, and the integral S3. It's 1 and 2, the end caps. These right here, they're going to be relevant. And the barrel part isn't going to matter. It's going to be 0, okay? Now, on the right-hand side, you have 1 over epsilon naught. Instead of it being rho, now it's area, so it's going to be sigma. And instead of this being volume, you're adding up over an area, and sigma is going to be constant. We're going to assume that this is a uniform charge density. So what that means is that really the area that you have over here is the same as the area of the end caps. We'll call A. All right. Now let's look at our little surface integrals for our end caps. Well, again, when you do the left-hand side of this, it's, E dot n hat, ds, okay? And the thing is that we know that the electric field E and the direction of out are parallel to each other. Again, we know that the electric field across the surface is uniform and constant in magnitude, which means that I can pull the E out. The dot product obviously is just going to give us 1. And now again, you're just looking at whatever the area is here, which is A. So each one of these end cap integrals here is going to give you E times A. So I have a E times A plus an E times A is equal to 1 over epsilon naught sigma times A. Okay, so if you look here, the A's cancel, and your electric field here is sigma over 2 epsilon naught. Okay, so pretty important result. Now, again, as we noted last time, it's constant. So how does this apply to conductors? Okay, specifically, and I want to remind you, the conductors that we're looking at right now fall up under the same realm as all the other stuff that we've been dealing with. We're dealing with electrostatics, so there are no active charges that are moving through the conductor. The change in charge over time over the surface of the conductor is zero. So, any charges that are sitting around or stationary, they had enough time to come to rest. So let's look at situations like that. All right. So, let's just pretend that you have this sort of region of conductors sitting around. No, maybe there's no charge on it. And what I'm going to do is to look at what the electric field on the inside of this thing is. Okay. So I'll just draw some sort of surface on the inside. Okay. So there's my surface on the inside of this conductor. So this is metal or something like that, blob of metal. And I'm going to use Gauss's law. E dot ds, or not dot ds rather, E dot n hat ds is equal to 1 over epsilon naught, the integral of rho dv. Here's the deal though. Conductors have an equal number of protons as they do electrons. Okay, the atoms on the inside of there. Assuming that things are not moving around, you will have an equal number of P's and E's, which means that when you look at the total charge that's enclosed inside our Gaussian surface, it's zero. And what that means is that on the inside of our conductor, our electric field is zero. Now, what if I polarized this thing? What if I took and I got a big old chunk of charge here and got it close to it? We'll pretend it's positive. We know what's going to happen is that all our free electrons are going to come zooming this way, and you'll have a glut of electrons on this side right here, and then you'll have a whole bunch of positives on this side right here that are left because all their little companion electrons went zinging this way. But the thing is that if I draw my surface right here, just a little beneath the surface of our conductor, and I look at how many pluses and how many minuses that I have, again, things add out and give you a net charge of zero on the inside. It's still electrically neutral, which means that the electric field on the inside of this thing is zero. Okay. Now, there are other arguments that you can make to demonstrate that. For example, let's pretend that there was a little bit of negative charge here. Well, that negative is going to hunt around and try to find a positive to group up with. The reason is because any other negatives that are sitting around here are going to want to push it away. Any positives that already have companions might pull it towards them, but it won't be able to hook up with them because, atoms, unless they're ionized, are electrically neutral generally. So what that means is that the place to look for charge is not on the inside of the conductor, but actually on the outside. Okay? So on the inside of a conductor that is electrostatic, one in which even if you've given it charge, that charge has had a chance to sort of relax and not move around, your electric field on the inside is zero. Not only that, the charge sits on the outside. Okay? Now, we can actually use that to talk about what the electric field looks like very close to the surface of one of these things. So for example, let's pretend that, I grabbed this little bit right here. What I'm going to do is, let's see, can I even do that? We'll do it this way. I'm going to zoom in here and I'm going to look at this curvy bit right there. Okay. Now, so if I were to take and, whoops, I don't want to do that. Let me fix that there. If I were to take and zoom it out like this, okay, what you'll notice is that as you get closer and closer and closer to your little surface here, things become more and more flat. So for example, now I'm going to keep zooming in. I'm going to zoom in right here. Okay, so that looks something like this. So let me take that and zoom it. You see how it's getting flatter and flatter? Well, the idea here is that no matter how curvy this is, if you zoom in close enough, eventually you're going to get so close that things are going to look straight. They're going to look flat. So if you think of this as a sort of a three-dimensional object, the surface is going to look like a flat surface like this, or, like a plane of charge. Okay? So if you were to look over here and zoom in, and what we'll say is we've zoomed in very, very, very close here. Here's the surface of our conductor. And, maybe sitting on the surface of our conductor right here, we have negative charge, we'll say. It's electrostatic, so it's at rest. So here's the surface. This right here is inside. And this is outside. The electric field on the outside is going to point outwards like this, exactly like that of a long sheet of charge. On the inside, though, the electric field is going to be zero for arguments that we made right here, where any charge that would be sitting on the inside is going to naturally migrate outwards because it's going to be pushed outwards. Okay? The electric field is zero on the inside. So what that means is that if I were to do exactly the same thing that I did previously with our sheet of charge, so here's a cylinder sort of poking through, you have a surface charge density here of sigma, and you look at your Gaussian surface, and if you remember, previously, this would be end cap 1 S1, this is S2, and this is the barrel side, this is S3. Well, S1 and S2 would have the same areas, but here's the deal. There's no electric field here, so there's no E. So when it comes to adding up the fluxes, the only flux that's going to matter is going to be the fluxes on this one right here. It's leaving. And again, the surface normal is in this direction, the electric field is in this direction. So when you take and you add up your flux contributions, it's just this one end cap that matters, which would be E times A. Okay? On the right-hand side, again, you have your 1 over, epsilon naught, the integral of, rho dA. But again, assuming a constant charge density, which would be true because we've let this thing come to rest. Remember, it's electrostatic. This would be sigma times A. So the A's cancel, and what this says is that very close to the surface of a conductor, the electric field looks like sigma over epsilon naught, whatever the charge density is over epsilon naught, and that's it. Okay, and the nice thing also is that we know that it always points straight out, perpendicular to the surface. So if I were to go back over here and take a look at this weird shape right here, I could very easily draw what the electric field would look like. All I need to do is to look perpendicular to the surface, like this. This is negative. It would go in, because that's what negative electric fields do, is they go into the charge. Okay? So this is a very powerful result right here. And what it does is to allow us to talk about the electric field due to a conductor very close to it. Now, as time goes by, we're going to relax the condition that we're dealing with an electrostatic situation and start talking about the dynamics of the situation, which we call those electrodynamics. And roughly around that time is also when we're going to start meandering in the direction of talking about the magnetic field, because the magnetic field is in part a consequence of charges that are moving. Okay, and I will see you then.